Have you ever stopped to think about how we describe things that have both like a size and a direction?
Hmm.
Like the path of a rocket
Uh-huh.
or the force of the wind,
Yeah.
or even how colors blend.
Interesting.
They all involve something more
Right.
than just a simple number.
That's where vectors come in.
Okay,
Would
vector.
capture both the magnitude and direction.
And the world they live in is a vector space.
Uh-huh.
So is a vector space just like a cosmic parking lot for these vectors?
That's a fun image.
I'm guessing it's more complex than that.
It is a bit more complex, but the idea of a designated space is spot on.
Okay.
Think of it this way. Imagine a map. Instead of cities, you have arrows pointing in different directions with different lengths.
Okay.
That gives you a visual sense,
Yeah.
a set with rules for how these vectors can interact.
So it's not just a random collection of arrows.
It's not random at all.
There's a structure.
Exactly. Like
Right.
a game with rules.
Got it.
And these rules are called axioms,
Axioms
and they determine how things work.
within the vector space.
Yeah.
Can you give me an example of one of these axioms?
Sure, let's take closure under addition.
Okay.
This means if you take any two vectors from your space
Yeah.
and add them together,
Mm-hmm.
the result must also be a vector within that same space.
So it can't escape the space.
Right back to our map analogy.
Okay.
If you follow one arrow, then another, you always end up somewhere on the map.
Right. You're still on the map.
Exactly. You don't suddenly end up in a different dimension.
Right.
That's closure.
So if I have two vectors representing forces on a bridge,
Uh-huh.
adding them together has to give me another force vector
Yeah,
relevant to the bridge.
right.
I can't end up with a vector describing the price of tea in China.
That's a great way to put it.
So it makes sense.
It highlights how these axioms ensure that our vector space behaves in a consistent and predictable way.
So they're kind of like the guardrails that keep everything working within the system.
Yep.
Why are these vector spaces so important in math?
Well, think about it.
Yeah.
Linear algebra, the branch of math that deals with vector spaces, is essentially the language of transformations.
I understand.
Stretching, rotating, warping, you name it.
So like those filters on photo apps that make your face into a cartoon,
Exactly.
that's using vector spaces.
The app is applying linear transformations to the image data.
Wow.
And vector spaces provide the framework to understand and control how that warping happens.
Okay, that's starting to feel more real world
Yeah,
than just abstract arrows.
sure.
What about like eigenvalues and eigenvectors?
Hmm.
They always seem so intimidating.
They might sound intimidating,
Yeah,
but they're actually incredibly useful.
really.
Think about how Google ranks web pages. It uses eigenvectors to identify the most important pages
Wow.
based on how they link to other pages,
Okay.
or how a guitar string vibrates.
Yeah.
The different modes of vibration are determined by eigenvectors.
So eigenvalues and eigenvectors aren't just some theoretical math puzzle.
No, they're not.
They're like built into how we search the internet and experience music.
Exactly.
That's pretty cool.
It is.
So we've established that vector spaces are a big deal in math.
Yeah.
But what about beyond equations?
Well, that's the amazing thing.
Yeah.
Vector spaces are not just theoretical constructs.
Right.
They have countless applications in the real world, like in physics.
Okay.
Vectors are used to describe motion, forces acting on objects,
Okay.
the behavior of electric and magnetic fields,
Wow.
even the intricacies of quantum mechanics.
So physics basically runs on vectors.
Pretty much.
Mind blown.
What about other fields?
Yeah, where else do they show up?
Everywhere. Think about engineering. Designing a bridge requires understanding the forces at play,
Right.
all represented as vectors.
Okay.
Or how about computer graphics?
Yeah.
Every 3D object in a video game or an animated movie
Uh-huh.
is ultimately made up of vectors.
Okay. And their movement and transformation rely on the principles of vector spaces. Wow. I never realized how much of our digital world is built on this foundation.
It's pretty amazing.
It makes you wonder, are there any limits to what vector spaces can be used for?
That's a good question. That's a question that keeps mathematicians and scientists busy,
Yeah.
exploring all sorts of new frontiers.
Okay.
But let's go back to the fundamental axioms we were talking about.
Okay. The guardrails of the vector space game.
Exactly.
We talked about closure under addition, but I'm curious about the other rules
Sure.
that govern how vectors interact within this space.
Well, another key axiom is commutativity of addition.
Okay.
It simply means that the order in which you add vectors doesn't matter.
Okay.
So adding vector u to vector v gives you the same result as adding v to u.
That sounds pretty intuitive.
It is.
Like if you walk one block north and then one block east,
Yeah.
you'll end up in the same spot as if you walked one block east and then one block north.
Exactly. It might seem obvious.
Right. But remember, we're establishing the fundamental rules
Got it.
of this mathematical system.
Okay.
And then there's associativity of addition.
Okay.
This tells us that when adding multiple vectors, it doesn't matter how we group them.
Okay.
So adding u and v first and then adding w is the same as adding u to the sum of v and w.
So it doesn't matter the order or the grouping.
Right.
What about scalar multiplication?
Great question.
How does that fit into the rules?
We have axioms for scalar multiplication too.
Okay.
Remember, scalar multiplication means stretching or shrinking a vector
Yeah.
by multiplying it by a regular number.
Right.
One important axiom here is distributivity.
Distributivity.
It ensures that scalar multiplication plays nicely with vector addition.
Okay.
In other words, if you multiply a scalar by the sum of two vectors, it's the same as multiplying the scalar by each vector individually and then adding the results.
So if I double the force acting on a bridge.
Yeah. It's the same as doubling each individual force component and then adding them together.
Exactly.
Right.
The result is the same whether I distribute the scalar multiplication or add the vectors first.
That's right.
These axioms might seem simple,
Yeah.
even obvious at times, but they're the bedrock that allows us to build incredibly complex mathematical structures
Right.
and solve real-world problems using linear algebra.
It's amazing how those basic rules can have such far-reaching implications.
It is.
But I have to admit, when I hear the term vector space,
Yeah.
my mind still goes to something abstract.
Sure.
Is there a way to think about it that feels more tangible?
Absolutely. Remember our map analogy.
Yeah.
Well, the space we live in, three-dimensional space, is itself a vector space.
Okay.
Every point in space can be represented by a vector.
Okay.
And we can use vector addition and scalar multiplication to describe movements and relationships.
Within this space.
Yeah.
So my morning commute is basically a series of vector additions,
In a way, yes.
with each change in direction or speed
Uh-huh.
representing a new vector
Right.
being added to my current position.
Every time you change direction or speed, you're essentially adding a new vector to your current position vector.
Okay.
This is a great example of how even something as simple as moving through space
Yeah.
can be understood using the language of vector spaces.
That's a cool way to think about it.
It is.
So even though it's this powerful mathematical concept,
Uh-huh.
they're really all around us.
They are.
I'm realizing there's probably a lot more to learn about the specific workings.
There's always more to learn, but
Yeah.
that's the exciting part of mathematics.
Right.
It's a constant journey of exploration and discovery.
I'm definitely enjoying the journey so far.
Good.
Are there any other key concepts related to vector spaces that you think are essential for understanding how they work?
There's one that's really fundamental,
Okay.
the concept of a basis.
A basis, that sounds intriguing. Can you tell me more?
Imagine you have a set of building blocks.
Okay.
You can combine these blocks in different ways to create all sorts of structures.
Right, like those construction toys where you can build anything.
Exact.
From a simple tower to a giant spaceship.
Uh-huh. With the same set of basic pieces.
Yeah.
Well, a basis for a vector space is like a set of building blocks for that space.
Oh.
It's a set of linearly independent vectors that can be combined to create any other vector in that space.
Okay, hold on a second. You said linearly independent.
Yes.
What exactly does that mean?
Think of it this way.
Okay.
If you have a set of directions, say north, south, east, and west, you can't combine north and south to get east.
Right, they're independent directions.
Right. In the same way, linearly independent vectors are vectors that can't be created by combining other vectors in the set.
Okay.
They each contribute something unique to the mix.
So a basis is kind of like a minimal set of ingredients, each one essential, that allows you to create any flavor you want
That's a great analogy.
within that vector space.
A basis provides both independence and completeness. It's a set of vectors that are distinct from each other and comprehensive enough to represent everything within the space.
That's pretty powerful.
It is.
But how do we actually find a basis for a given vector space? Is there some sort of recipe for that?
There are actually several methods for finding a basis.
Okay.
And the specific approach often depends on the particular vector space you're dealing with.
Makes sense.
But the key idea is to find a set of vectors that are both linearly independent and span the entire space.
Span the entire space. I'm not quite sure I follow.
Spanning the entire space means that every vector in the space can be expressed as a linear combination
Okay.
of the vectors in the basis.
Got it.
In other words, you can build any vector in the space by combining the basis vectors in various ways,
Okay.
just like you can build any structure you want,
Right.
using the blocks in your construction set.
So a basis needs to be both independent, like our distinct directions, and comprehensive enough to create anything within the vector space through linear combinations.
Exactly.
That makes a lot of sense.
It's one of the key reasons why vector spaces are so versatile.
Okay.
They provide this framework for breaking down complex objects into their fundamental components,
Yeah.
and then understanding how those components interact.
It's making me think about all those applications we discussed earlier.
Yeah.
Like physics, engineering, computer science. Are bases used in those fields too?
Absolutely. In physics, for example.
Okay.
You might use a basis to represent the different directions of motion in a system,
Okay.
or in computer graphics.
Mm-hmm.
A basis might be used to define the orientation of an object in 3D space.
So bases are like this underlying structure,
Yeah.
this invisible scaffolding that supports all these incredible applications of vector spaces.
That's a great way to put it.
Wow.
They're the foundation upon which we can build and analyze complex systems and solve real-world problems. They're essential for understanding the shape and behavior of these spaces.
This is also fascinating.
It is.
It's like we're peeling back the layers of this mathematical onion. And with each layer, we discover something new and amazing about how vector spaces work.
It's true.
It's clear that there's so much more to learn about bases.
There is.
And how they're used in different contexts.
Yeah, but that's the beauty of mathematics.
Right.
The more you explore, the more you discover its intricate beauty and vast potential.
Well, I'm definitely hooked.
I'm glad to hear it.
You've sparked my curiosity to delve deeper into this world.
And speaking of delving deeper,
Yeah.
there's another key concept we should talk about.
Okay.
Dimension.
Dimension.
It's closely related to bases.
Okay.
And helps us grasp the size of a vector space.
I usually think of that in terms of like physical space.
Oh,
Like the 3 dimensions we move around in, length, width, and height.
you're on the right track.
Okay.
In our everyday experience, we think of 3 spatial dimensions. But in mathematics, the concept of dimension takes on a more abstract meaning.
Okay. I'm intrigued. How do we define dimension in the context of vector spaces?
It's actually quite simple.
Okay.
The dimension of a vector space is simply the number of vectors in a basis for that space.
Wait, so if a basis is like a set of building blocks for a vector space,
Yeah.
the dimension tells us how many blocks we need
Yes.
to construct anything in that space.
Exactly. In our 3-dimensional world, we need 3 basis vectors to describe any point in space.
Okay,
That's why it's called 3-dimensional.
that makes sense.
We often use the familiar x, y, and z axes as our basis vectors.
So our world has 3 dimensions because we need 3 basis vectors to describe any location within it.
That's right.
What about other vector spaces?
Yeah,
Can they have different numbers of dimensions?
absolutely. Vector spaces can have any number of dimensions,
Right.
from 0 to infinity.
Whoa, infinity. So a vector space could have 1,000,000 dimensions or even an infinite number of dimensions.
Exactly.
Yeah.
Of course, vector spaces with incredibly high dimensions
Yeah.
are usually found in more abstract areas of mathematics and theoretical physics.
So?
But the core concept of dimension remains the same.
Right.
It tells us how many basis vectors we need to span or completely describe the entire space.
This is making me realize that vector spaces are way more diverse than I initially imagined. They're not just about describing physical space.
Right.
They can represent all sorts of abstract relationships in complex systems.
You're absolutely right, and that's what makes them so powerful.
Yeah.
They provide this incredibly versatile framework for understanding and manipulating data.
Wow.
Whether it's describing the motion of planets, analyzing economic trends, or building sophisticated algorithms.
I'm starting to see how understanding dimension can give us insights into the complexity of a system or a problem.
Yeah.
The higher the dimension, the more degrees of freedom or independent variables we have to consider.
Exactly.
It's like adding more building blocks to our set, which means we can create more complex and intricate structures.
That's a great insight dimension. Gives us a way to quantify the size or complexity of a vector space, which can be incredibly useful in a wide range of applications.
I'm so glad we delved into this. The concept of dimension is definitely something I'll be pondering for a while.
As you should. It's one of those fundamental concepts that pops up all over mathematics and science.
This whole journey through vector spaces has been amazing.
I'm glad you're enjoying it.
It's incredible how something that seems so abstract at first
Yeah.
turns out to be so connected to how we understand the world.
It really is.
And we've only scratched the surface, right?
We've only just begun.
Okay, now you've really got me curious.
Good.
What else is out there?
Well, we could delve into the world of inner product spaces.
Okay, inner product spaces.
Imagine taking our vector spaces and adding the concept of angles and lengths.
Okay, so we could start talking about orthogonality,
Exactly.
whether vectors are perpendicular and projections.
Yes, like shining a light and seeing the shadow of vector casts.
That sounds pretty visual.
It is. Inner product spaces are essential for understanding concepts like distance and similarity.
Between vectors.
Yeah, which has huge implications in fields like machine learning and data analysis.
So vector spaces are like this super adaptable framework
You got it.
that can be customized.
That's one of the most remarkable things about them.
Wow.
We can equip them with additional structures and properties, like inner products or norms, to tailor them to specific needs
Okay.
and applications.
Speaking of applications,
Okay.
we talked about how vector spaces are used in physics, engineering, computer science.
Yeah.
Are there certain types of vector spaces that are more important in some of those fields?
Absolutely. For instance, in quantum mechanics,
Okay, the tiny particle.
the mind-bending world of subatomic particles,
Right.
they use something called Hilbert spaces.
Hilbert space.
These are complex vector spaces with an inner product.
Mm-hmm.
And they're the foundation for describing the bizarre but fascinating behavior of quantum systems.
So the fact that a tiny particle can be in multiple states at the same time, or that things can be entangled across vast distances,
Yes.
that's all based on vector spaces.
It really is.
That's wild.
And then you have engineers who often work with finite dimensional vector spaces,
Okay,
which are easier to handle computationally
makes sense.
and have direct applications in areas like signal processing and control systems.
It's just incredible to think that these abstract mathematical concepts are behind so many technologies we use every single day.
It really highlights how powerful these mathematical tools can be.
Yeah.
Vector spaces are like a hidden language that permeates so much of our modern world,
Right.
from smartphones in our pockets to the algorithms that shape our online experiences.
This whole deep dive has been a real revelation.
I'm glad to hear it.
I feel like I've gained a new appreciation for the beauty and power of vector spaces. But it's clear that I've only just begun to explore this world.
That's the beauty of it, really. There's always more to learn, more connections, to make more depths to explore.
Wow.
And as you continue your journey, you'll find that vector spaces offer this incredibly elegant and powerful way to understand and model the world around us.
Well, you've definitely inspired me to keep learning.
Good.
Any final thoughts for our listeners?
I'd say embrace the wonder of mathematics.
Okay.
Don't be intimidated by abstract concepts.
Right.
Keep asking questions, keep exploring, and you'll be amazed at the insights you uncover.
Wow.
Vector spaces are just one example of how powerful and far-reaching mathematical ideas can be.
Yeah.
You never know what incredible discoveries are waiting just around the corner.
That's fantastic advice. And on that note, we'll wrap up this exploration of vector spaces. I hope you've enjoyed the journey as much as we have. Until next time, keep exploring and keep asking questions.